attachment to the structure to facilitate either directly or indirectly to attach the slings. Lift point design load. Lift point design load shall be taken as the maximum sling force, including dynamic load factor, that's a DAF, dynamic amplification factor, COG shift effect, and skew load effect, and then contingency factors. Let's see one example of simple lifting paradigm. This is the main plate and cheek plate. This is the paradigm board hole you can see, and then this is welded. Cheek plate is welded to the main plate. Here you could see cheek plate, weld the main plate. Simple thing. Purpose of lift points. Why do we have this kind of lift points? Jacket or deck fabricated in the yard will be installed using lift concept and require either pad or training as the designer plans for it. If you see here an example, this is the structure. This is the jacket structure. Here we are the lift point. We are using the slings to lift it and install it at the offshore. So this is the main purpose of the lift point. Upending. Upending is required for jackets fabricated in a horizontal position, and then it requires to be made vertical either in the yard or in the final installation location. Usually at the site, upending will be done in water, and in some cases of small height jacket, it may also be upended in the yard or transported in vertical condition. I'll show it here on example. Here you see is the jacket lifted and placed. Jacket upending in water. This is the jacket lifted horizontally and put in water, and then using the slings, it's being upended. It's made in the vertical position. That's what it's explained here. Usually at the site, upending will be done in water, or in some cases of small jacket, it may be upended in the yard and transported in vertical position. You could see here also. This is the upending in air. This is the yard. This is the jacket fabricated in horizontal position, and then it's using trailer crane and the front crane, leading crane. It's being upended vertically, and then it's made vertically, and it will be transported vertical position. That's what it said here. Hope it's clear. One sample spreader bar you could see here. It has the lift points, and below also we have the lift points. This spreader bar is mainly like to spread the load. Actually, the slings will be here when we have something structure having a lot of equipments and we want to clear sling passage, and then we use the spreader bar to spread the load, and from here the slings will be connected onto the hook. Here you can see one simple example. Here is the force, and this plane, what is green color plane, it will be a tensile plane, and bearing stress will be here. It will have the bearing stress, and combined stress will be there, and shear stress on this surface also it will be there. Half the weld length 2 times r radius. Let's omit this for conservatively. And forces etc. during lifting. Self-height, dynamic load, impact load, wave and current loads, and wind loads. When we are lowering the jacket structure on the water, waves and current loads also it will be experienced by the jacket structure. Lifting versus upending. During the lifting operation, most of the time, the sling forces remain constant throughout the operation. Here you could see here in the slings. These are the slings, lifting slings. Here, most of the time, the slack force is constant in this operation because this jacket weight it's hanging vertically. So when it's entered into the water, there will be some added force because of buoyancy. But most of the time, all these force lengths will be having the constant forces specific to each line. But during operating operation, the loads and the direction of load changes continuously. It would change continuously as the jacket gets rotated. Hence, it becomes complicated to estimate the critical load and direction. So most of the time, here you see when it is getting entered, some slings will be in larger slack. Here you can see the slack of these slings also clearly. Here these slings, top slings not taking much load. The bottom two are taking more load, and below also it will be taking more load. So during since it's getting rotated, it will have different loads at different stages of operation. So what say here it becomes complicated to estimate the critical load and direction. And opening in water, you could see here it's placed on water and using these lifting points it will be slowly lifted up and it's kept in the 90-degree position. That's the updated position. So concept wise, if we see the PARE design guidelines, the following guidelines and overview of PARE design based on DNV rules. Okay, DNV states two key slicing rules. So we need to see the slicing rules we need to be of how about it. The diameter of the holes in the pares match the circle used. Here you see this is the circle, and this is the diameter of the hole. Clearance between the circle and the pin and pare hole shall not exceed 6% of the circle pin diameter. So at this location we have the pare hole and sling pin circle. So clearance between the circle pin and this pare hole should not exceed 6% of the pin diameter. So what is what the pin diameter is there? The clearance should not go more than 6%, and because of the pare at the hole shall not be less than 75% of the inside width of the joining circle. So when we take a cross section here, this will be the main plate, and cheek plates also will be there. This will be the jaw width for this circle. If we take the plan of 75% of the inside length to the thickness of pare hole shall not be less than 75%. That means this jaw width it should be almost 75%. This main plate and cheek plate should be character design of pare should be factored based on the particular load application. For right lifting ankles, a symmetric pare design should be used. For multi-point lift, as in offshore container or frame, the non-symmetric design can be used. If required, plated supports can be added to symmetric design. Plated supports, especially for this main line supports. If you see the trunnion, this is the tubular. It's welded to the skin tubular internal length. Where the force comes, we are resolving it horizontal or vertical. This is the slide. Slotted into the tubular. Spice this slotted into the tubular. You can see this construction here. Design procedure first. Establish the maximum sling load. So we need to find out the maximum sling load and select a suitable sling diameter and select suitable circle. So sling load, sling diameter, sling suitable circle, check the suitable suitable main plates than cheek plates. Check suitability of spacing, gap with the selected circle, and add spacers if required. Allow the structural analysis for strength and modify the para or circle as necessarily. Let's see. Generally, one main plate thickness from 1 to 90 mm can be used. One main plate generally. Cheek plates should not be more than the thickness of the main plates. It should be constructed. Cheek plates should not be more than one cheek plate. Each face shall be avoided. Second, cheek plates shall be considered as a spacer plate. Pouring shall be done of cheek plates. This is our main plate. Then cheek plate will be welded. Then 5 mm shall be provided between cycle and the cheek plate spacer plate. So here we will be having the cycle. So minimum space, 5 mm space. So we space shall be provided between the main plate and the underside of the circle. This aluminum for multi-point, it's essential that rays point directly with point center to prevent any lateral bending moments on the rays. DNV suggests the tolerance of as allowable misalignment. Rays rated above and capacity cheek plates must be fitted to reduce the pain in the circle direction. These must be fitted as additional plates welded onto the padai profile, not a single boss as one figure. This is the right thing. Padai materials. Certified engine 3.1 material certificate. Padai welding. All padais must be welded primary structure by use of full penetration walls. It is a good if welding directly onto the horizontal plate of the body must be specified EM Z grade to prevent lamination of inside board. When sizing the cut body unification, maximum 14 blast load, load tester cameras, DAF, drag load on it when lifting equipment. So here you can see the clearances. This is the clearance we need to see. The C2 should be almost 1.5 times the diameter of the sling. C2 should be greater than 1.5 times the diameter of the sling. We need to check this space. Yes, at least 5 mm we need to keep it. Symmetrical arrangement using here. And this, if the body force is like this plane will be shear. First you understand this is the broad shear plane. It's the main plate. And cheek plate is DC. FP is the force. Stiffener. This is the structure. Next thing, main plate. This is the sling stiffener plate and cheek plate. Out of plane force 5% in addition to FPL cost theta. This cross section you can see here, two stiffeners, main cheek plate, main plate and two cheek plate and spacer plate kind of thing are been bearing stress calculation. If you see whatever the force FPDDL is a parallel design load divided by diameter of the pin 2 times thickness of the cheek plate, main plate and RF. Here you can see this is the force diameter of the pin, cheek main plate and 2 cheek plate thickness, and RF is the reduction factor. We need to see what is this reduction factor as well. And load shear stress, whatever this force, and these two plane. So 2 times Rm minus Rp. Rm is the main plate radius, Rp is the this whole in radius of main plate radius, cheek plate radius. So Rm minus Rp into the main plate 2 times, because there are two cheek plate, 2 times Rc means cheek plate radius minus pin radius times thickness of cheek plate. So this is the load shear stress. Then tensile stress section at section PP. If we see this section PP here, main plate plus cheek plate also it's there. That's the tensile stress. FDL sine theta, because we are taking this force in this vertical direction. So FV is the force into sine theta. That's the times Rm minus Rp into thickness of main plate. And that's one plane from here to here, Rm minus Rp. That's this area of main plate 2 times, and cheek plate will be 4 times. 4 times radius of cheek plate minus pin minus thickness. Then just cross section QQ. QQ is this section cross section. If you see, there are two difference plus main plate also there. So this complete cross section. That's CFB sine theta to B times thickness of main plate 4 times BS plus TS. That's a stiffener. And in plane shear stress, horizontal shear stress at section PP is same as this value it will come. And horizontal shear stress at section QQ is that mainly this B times thickness of main plate, because main plate only it would be taking most of the shear, not this stiffness like a minimum kind of thing. So for horizontal shear at section QQ, it will be B times this thickness of main plate. That's what is considered here. Then in bending stress, we can consider F this horizontal F arch into this dial arch. F arch is a force, arch is the lever arm. So that's the moment. F arch into arch, that force also you can see in plane, that's a cos theta force, right? So F dTL into cos theta and arch. So 2I by B is this width. So we can say IXX. We can calculate even out of plane also the same way. Arch is the lever arm. Then we can calculate the combined stresses in plane bending moment plus out of plane bending moment square. That's the bending stress, combined shear stress in plane out of plane, and bond mass stress is tensile stress plus shear stress 3 times shear stress plus bending square minus FT and FB. This is the combined bond mass stress. Once we know all these things, bearing stress we can take a level 0.9 and tensile shear stress 0.4, tensile 0.6, bending stress 0.6, combined stress 0.75, one minus also 0.75, we can consider it conservatively. Welding between the main and cheek plates. This is the weld size. This is the main plate and these are the cheek plates. So main plate thickness, main plate radius, first plate cheek plate thickness, first cheek plate radius, second cheek plate thickness, second plate radius. This is the force R1, R2, R1. That's a 0.5 times 50% of the whatever the design spring load. So this is the area where it's getting the forces transmitted. So force transmitted between the main plate and first cheek plate, that's the R1. Main plate and first cheek plate, that's force into main cheek plate and total thickness. Cheek plate 1, cheek plate 2, main plate. And weld size, that weld size required between the main plate and first cheek plate is R1 plus R2. That's the force. R1 plus R2 2 pi RC, that's the circular portion 0.7 times 7 into Fy, yield distance of weld. Force transmitted between the first cheek plate and second cheek plate. R2 is thickness of second plate, cheek plate. The same way with fillet weld size required also we can find it out. Unsymmetrical arrangement. Many occasions we will be using the unsymmetrical arrangement. Vertical load distribution across the main plate is not uniform. It introduces additional eccentricity. We can see this though if it is the case. Here will be this centroid, and this additional eccentricity also has to be considered for this vertical force. This horizontal force moment about this point, if we take a moment, this horizontal into H, this F into E. Thus, we need instead of connection to the main structure, the load from the parallels will be transmitted to the main structure safely without overstressing. Many different methods of transmitting forces can be adopted, but a simple way of transferring is by either by direct shear or by ring shear. Methods using bending or combination of axial bending shall be avoided. So parallel main plate slaughter to the deck extension. If it's slaughtered here, you can see these are the welding between the tube and main plate. So yeah, that's the length F being detail into sine theta, that's vertical, 4 times, because there are 4 times, so tubular 0.4 times Fy plus this vertical plus additional eccentricity is causing, right? Eccentricity plus d by 2. That's additional moment. 2t into t minus f detail h. This will be h will be the opposing, and this will be the opposing. That's why it's reduced. Or I brought slaughter to the deck extension. It can be slaughter like this as well. Here there is no eccentricity, but here there is eccentricity, so that's why this eccentricity portion is coming into picture. Here parallel plate welded to the, here it's welded to the skin, like skin. Only vertical load transferred. This lines. Moment is taken by this stiffness. Main plate welded to the skin tube. The vertical component of the load is transferred through the direct shear between the main plate and tube. Horizontal component and moments shall be decoupled between the top and bottom ring plates. These forces on the rings shall be transferred as a circumferential shear, as the rings shall be complete. Otherwise, these forces shall have to be transferred by the bending. Top ring plate. This is the force. Cos theta 0.5 times L by H by L. This is the calculation of ring force, how to resolve between the top flange and bottom flange. And then final terminals will be add out when no redundancy in design failure of the component will result in catastrophe or multiple unclear load path. Mean manual calculation too conservative due to the assumption made on load path. The manual calculation becomes too complicated if you must give us maximum load path. Indicates hotspots where stresses are high. Here you could see this is the parallel, this is the ring stiffness. These kind of complicated things we can do it in the FEM. So this is how this lifting parallel is. Lift points are designed. Lift points are designed based on this.